Hello everyone, my name is João Ferreira and I'm a master's student in Physics Engineering at Instituto Técnico of Lisbon and a researcher at CEFEMA. Today, I'll be presenting my master's thesis topic, typicality and matrix product states. These words may seem a bit daunting, but I'll guide you through them. So, let's start. First of all, I'm a researcher in theory of condensed matter, which is the area of physics that describes the collective behavior of quantum particles, like atoms or electrons. It's the same area that describes states of matter or underpin the development of silicon chips inside your smartphone or computer. In particular, I study many body systems, which, just like common materials, are composed of many quantum particles interacting with each other. The best tool to describe multiple quantum particles is a quantum state. Consider an electron, which can have a spin pointing upwards or downwards. In general, the electron can be both in a quantum state up or down with a given probability p up or p down. To describe two electrons, we need four probabilities, since electrons can be both up or down, the first up, second down, and vice versa. If you want 10 electrons, we need 1024 probabilities, and for 20 electrons, we need 1,048,576 probabilities. Clearly, adding particles increases the complexity of the problem at hand. As a physicist, we are more interested in knowing the properties of these states, such as their energies. We can compute the energy of two electrons using only paper and pencil. For 5 electrons, we would need 7 seconds with an old mobile phone chip. Around 15 electrons would take less than 1 hour in a modern PC, and the energy of about 20 electrons can be computed in a couple of days using a supercomputer. More than that, and there is not enough computer power in the universe to achieve it. Clearly, we need a better tool if we want to study realistic systems, which usually have billions and billions of atoms. Matrix product states is that tool. Think of a matrix product state as a JPEG compression of a picture. The JPEG format uses less bits to represent the same image, losing some details, but keeping the main characteristics. An MPS efficiently compresses a quantum state using less numbers, but keeping the physical structure intact. This compression is controlled by the bond dimension parameter chi. If chi is not too big, we can work with bigger system sizes, like 200 or 400 electrons. MPS has been shown to work for systems in equilibrium, but we still don't know if it worked for systems out of equilibrium. My thesis aims to study this problem. To do so, I use a technique called typicality, which says that to understand the properties of a system with infinite temperature, it's enough to consider a quantum state with random entries. What do I mean by this? Consider we want to study how a many-body system conducts electricity. Usually, we'll have to understand how it conducts electricity for all given configurations or quantum states of the system. These are a lot. But if the temperature is infinite, we only have to compute the conductivity for a given quantum state, a random quantum state. Much easier. In my line of work, I studied the dynamic properties of systems using typicality with MPS instead of quantum states. If proven correct, my work could solve many open questions in today's field of condensed matter and pave the way for future developments in nanotechnologies. Thanks for watching.